Today's lesson is about specific heat capacity. It is the second type of heat transfer that we will have come across. There are quite a few things that we need to know in this topic, but some of them are common sense and will be very easy. The first thing is we need to know the difference between boiling and evaporation, something we often get confused. We need to explain what latent heat is and what specific heat is, and what is the difference between them. We need to know that latent heat of fusion is to do with melting and freezing, and latent heat of vaporization is to do with boiling and liquefying. We need to know the difference between specific heat capacity and latent heat, something we've come across before. We need to know that latent heat is associated only with change of state, and because of that, latent heat is about potential energy of molecules as it is about making and breaking bonds. And finally then, we need to know how to use a latent heat equation. Now, to go over the differences between boiling and evaporation. First of all, I want to use these pictures to try and pick out the differences between boiling and evaporation, and then to use them to help you to complete the table on the next slide. You can pause this slide at any stage and go backwards and forwards between this and the table. This part, we're going to look at the differences between boiling and evaporation. To help you do this, I've put some pictures up, and that will help you to work out the differences between boiling and evaporation. Use these pictures to complete the table on the next slide. You can pause this slide at any time and then go backwards and forwards between this slide and the next slide to complete the task. This is the table I want you to copy and complete to get the differences between boiling and evaporation. There are 6 features that I've chosen. The first feature I've done for you. Now the 6 features are, during the change of state, what occurs. The second thing is about the speed of the process. Is it fast or slow? The third thing is, would we see bubbles during either of these? Next one, where in the liquid does boiling or evaporation occur? And then, at what temperature does boiling occur and evaporation? And finally, where does the energy come from that is needed for boiling and evaporation? When you finish this, you can check your answers against the next slide. Now this slide shows the differences, the completed table showing the differences between boiling and evaporation. I'm not going to read all the answers out. All you need to do is to pause this slide and compare it with your version and to make any corrections that are necessary. Now, this slide is important because it contains the key facts about latent heat, and we need to make a permanent record of this, so please copy the 4 bullet points into your book. The first one is that latent heat is the energy needed for a change of state. Second is when a change of state occurs, the internal energy of the substance is changed, but the temperature isn't. Now, the key thing here with specific latent heat is that it is the amount of heat, whereas latent heat is just a generalized energy needed. So specific latent heat of fusion is the amount of energy needed to melt 1 kilogram of a substance without any change in temperature. And similarly, the specific latent heat of vaporization is the amount of energy needed to boil 1 kilogram of a substance without any change in temperature. So the key word there is specific, which means amount. Now, as you know, I keep coming back to this graph because it is so important to show the difference between specific heat capacity and latent heat. Latent heat, we said, is about change of state. So on the graph, this is the condensing, when the gas is turning into a liquid, and it is the freezing, when the liquid turns into solid. And the graph is characterized by the fact that it's flat in each case. In all other cases where it is sloping, this is to do with specific heat capacity. This is where energy is given to the molecules and their movement increases because they have greater kinetic energy. So in a solid, they vibrate more. In a liquid, they have greater freedom to change places. And in a gas, the molecules move faster. So really important this. I can't stress this enough. Again, another important piece of information, the latent heat equation. This is not an equation that you have to learn, and you will be given it on the formula sheet in any exam or test. What I do need you to do is to copy the equation, both the word version and the symbol version. I'd also like you to put it into a triangle form so that you can use. Now, finding the latent heat of fusion of ice. This is an experiment that we would do in class. Now, obviously we can't because you don't have the apparatus. But if you look at the equation, specific latent heat equals the energy needed for a change of state divided by the mass collected. Now, if we look at this equation, we should be able to determine what we need to measure to be able to get this latent heat of fusion. Now, if you look at the two things there, obviously we need to find the mass of ice that will be melted and how much energy was needed to do so. Try and think how you could do this. Using the diagram on the next slide will also help you. Now, the apparatus we're going to use to get the latent heat of fusion of ice, as you can see from the diagram, the most important thing is an electric heater, so you can work out the amount of energy. We have got a source of ice into which the heater is put. We have something to collect the water in, and we have a top pan balance. Now, try to think how you would do this, and try and think of the order in which you do things. You've probably worked out the main points of the experiment as it is because you're a bright group. So here's an outline plan. So the first thing you need to do is to warm the heater up. so that none of the energy is used to heat the heater up first of all, to bring it up to its working temperature. Once it's at that, put the heater into the ice for a set amount of time, so you can work out how much energy was used. From that then, you measure how much ice had melted and was collected in the beaker, which is on top of the top pan balance. Now, in true Blue Peter fashion, these are a set of results I got when I did the experiment. So the mass of the beaker when it was empty weighed 240.63 grams. The mass of the beaker and water which we collected from the melting ice was 256.48 grams. That means we'd collected 15.85 grams of water, i.e. 15.85 grams of ice had been melted. And to do that, we'd use 4,800 joules. Now we're going to use these results to calculate the specific latent heat of fusion of ice. Now, the main piece of work I want you to do is this. First of all, put the title, Specific Latent Heat of Fusion of Ice. Then, draw a diagram of the apparatus. Bullet point your method. Copy the table of results and then use the formula latent heat equals the energy divided by the mass. And don't forget, the mass has to be in kilograms, even though we've got it in grams. You can then work out the specific latent heat of fusion of ice and then check your answer with what I got on the next slide. Here is the answer I got, 303,000 joules. Notice I've rounded it because when you're looking at 300,000 joules, 839 joules is not a major component. Now finally, I'd like you to try and be able to answer these two common occurrences. 1. When we sweat, the sweating cools you down. And what is the link to latent heat? Secondly, if it's very cold, why would you not want to get wet? In your responses, I'd like you to use the words latent heat, particles, and energy. Right, this concludes the work on latent heat. I know you'll see there aren't many calculations, but the next lesson we're going to look first of all at latent heat calculations and then the higher level calculations which use both latent heat and specific heat capacity. See you in a couple of days.